Sure.
Hey, thanks a lot for having us back. This is really exciting to be on with so many people, and hopefully we'll be able to give you something interesting and useful today. Yeah, I'm Zach, and I started back at Wikipedia about 4 or 5 years ago at this point, and I knew that A/B testing was going to be a critical piece of our fundraising program. It was pretty much the whole piece of our fundraising program. As you know, you've seen the banners at the top of Wikipedia. That's how the Wikimedia Foundation, the organization behind Wikipedia, makes almost all of its money. And when I joined almost 5 years ago, there were just 20 employees and at the foundation, but there was a big plan for growth. We needed to build up a proper tech infrastructure and ops department and software developer, software feature department, as well as legal department and some extra administrative support. So there was a whole lot of stuff that was sort of overdue, and there was this big plan to where we were going to need to double our revenue every year for 3 or 4 years in a row. Since we didn't have a product to sell or anything like that, there was only one way that we could really increase the amount of money that we were bringing in, and that was to find better ways of asking on the website. And so let's see, I'm sort of getting ahead of myself here already. But facing that goal, we kind of thought about, okay, well, what are really the goals of our A/B testing program, and probably if you're running, and also I should say where we're coming from on this is we're not academics. We don't have PhDs in statistics or mathematics. We are, although Sahar does have a master's in computer science, but where I'm coming from this is I was a manager, and I needed to know that we were doing our A/B testing in the right way. I needed to know that we weren't making bad decisions. And I was a creative lead on the campaign too. I was coming up with ideas for the banners and for the stuff that we were going to be putting up there. And so I wanted to know that we were, not making really bad decisions based on some kind of flawed understanding of how A/B testing works. And and that's where we're approaching this from, this presentation from. Is we want to. I'm assuming that you're not coming to this presentation looking for an academic proof of some new, even better way to do A/B testing. What we're hoping to give you is walk you through the process that we went through at Wikipedia to get confidence that we were doing things correctly. And okay, so are these the goals of your A/B testing program? These were basically the goals of our program. We wanted to improve some metric, which in our case was donations per impression, but also amount of money per banner impression. And so people are seeing millions of banners we're able to put up. At Wikipedia, we have a huge amount of traffic every day, every week, and so we wanted to make sure that we were asking in a way that we were getting the most donations per million banner impressions or whatever. But we also wanted to do as many tests as possible. And we wanted to be able to find big breakthroughs, but also incremental gains. So we knew that if we had to double our income every year, that we needed to find some things that were going to make, a 10, 20, 50% difference. But we also wanted to be able to rack up lots of small gains, which we knew were hard to detect using A/B testing techniques. So this was me when I first started, and I was confused, and that's Megan Hernandez, who runs the fundraiser and still runs it today, and she was really instrumental in developing this program. So we had done a ton of tests, and Sahar joined us about 1.5 years ago. This is screen from our Google testing calendar, and Sahar had the hard job of digging through all of our past tests and doing a review of them. And I don't know, Sahar, does that bring back any bad memories?
No comment.
So we didn't always do a great job of keeping track of all of our tests, but this was just this was 1 week of our A/B testing schedule, and as you can see, every day we were doing multiple tests. And so the big question for us in A/B testing was not only how do we trust whether a winner is really a winner, and if a new winning banner wins by 5% or 10%, does that really mean 5 or 10%, or does it mean from 0 to 20%? Those were important questions. We wanted to be able to answer those. But the question that we really found a hard time answering, because it doesn't come up a lot in the literature, and it's not something that the experts we talked to and consultants that we talked to had very good answers for, was we wanted to be able to test with the smallest possible sample. In other words, we wanted to end our tests as fast as possible. And that was so that we could test more. Because if you look at this calendar page here, as much as we were testing, if we were able to do twice as many tests as this, because we had way more ideas than we were ever able to test. So if we were able to test twice as much, then we would be twice as likely to come up with new ideas or with new breakthroughs.
So this is an example of an early breakthrough that we found even before I joined the foundation. And you might remember the battle Jimmy banners staring at you. But after a lot of trial and error, we figured out that this top green banner with stacks actually did better. And that's an example of a big change getting a big win. But sometimes a small change would give us a good win as well. Here, if we made the bottom banner have one line that looked more like a link, we had a small, one of those small incremental gains. Lastly, sometimes we make a small change and it would make a big difference. So just this ugly cyan highlight would give us, I think it was a boost of 20 or 30%, I don't remember exactly, but it was one of the biggest wins we made in 2013. Now, some of you might be asking, and people walked up to us and told us sometimes, your banners are so ugly. Why is that? Well, part of it is ugly works. This is a real test that someone did in a dating site, and the more authentic, badly designed version had 180% difference. And I think there's a second reason, Zach.
Well, and also we don't have an actual full-time designer working on our team. It is very hard to find designers in San Francisco. So if you know any designers who would like to do, especially designers who would like to work on banner ads, which is the most unglamorous work for designers to do, then send them our way. But also we have the banners on Wikipedia, we never run ads on Wikipedia. We never have, and we never will. But people don't necessarily know that. So the minute something starts looking a little glitzy or nice, like an ad, people know how to ignore that. And that's true everywhere, but doubly true on Wikipedia. Okay, so now we're going to get into the basic concepts of A/B testing. Now, if you really understand already the basic statistics of A/B testing, it's okay if you go check some email right now and keep listening in the background and come back in 5 minutes. What we're going to try and do is lay out the basic concepts, and then we're going to wade into a controversy, an A/B testing controversy, and in which we take a scandalous side in this controversy, and then we're going to get deeper into the concepts. Because if you're like me, trying to get your head around these A/B tests, around these statistical concepts, even I'm good at math. I've worked as a software developer. I'm not completely technically void, but after studying stats textbooks and, reading the Wikipedia articles on all these concepts 800 times, I still had trouble getting my head around the concepts. And that's partly because almost all of the explanations about A/B testing, about statistical concepts in this area are usually used in other areas besides our particular application of A/B testing website. So a lot of the explanations, they all talk about populations and it's really all for scientists studying bugs, and astronomers studying stars and stuff like that. It's so to make the context switch, that's my pet theory anyways, is that part of the reason why it's so hard for people in our field to understand those concepts and why it's so hard for the experts to explain the concepts to us and for them to relate to our application is because our application is actually very different. At least it feels different. It uses different terms. Okay, so anyways, first let's just introduce the concepts that we're talking about, and then we'll dig into them deeper. So this is an online calculator. This is our favorite calculator that we've ever found because it just displays the results kind of nicely. And we don't have the URL there, but you can find it by Googling Thumbtack A/B testing calculator, and it'll come right up. And so look, this is just letting us put in the values from a test that we did on banner A and banner B. And in this hypothetical test, banner A got 500 donations out of 10,000 banner impressions. B got 550 donations out of 10,000 banner impressions. And we're putting in 95% confidence, 0.95. And so we want to be 95%. That's the social convention that we're signing up for by putting in 0.95. And these are the results with the Thumbtack calculator. And so you can see that what it's done is it's figured out that 500 donations is a 5% success rate for banner A, and 550 is a 5.5% success rate for banner B. Now, what are these ranges? Where does statistics come up with that? Those are the confidence intervals, and the statistics that we use for A/B testing is based on a whole bunch of assumptions that I did not trust. That's why I was scratching my head in that earlier picture, and I wanted to really understand them. And hopefully, we'll be able to. If you don't understand where those assumptions come from and how it's calculated, we hope that you will by the end of this presentation. But according to these assumptions that this field of statistics makes, it says that what it's sort of saying here is that if we ran this test over and over again in sort of a Star Trek time loop, in alternate universes or something, or more practically, if we just ran the same test with a similar user group every day at the same time of day, something like that, that we could expect that banner A would not always get a 5% success rate, but that 95% of the time, because we chose 0.95 on the previous page, that 95% of the time it would the response rate for banner A would be somewhere between 4.6% and 5.4%. So hopefully that makes sense, but if it doesn't, and I'm sure it doesn't completely make sense, but we're going to flesh it out as we go on through this presentation. And then you can see it's calculating a different range for banner B. And that nice graphic there shows you, visually that banner B is doing better. The range, or at least it's probably doing better, because there's a chance that, if we ran this test again, that banner A might get a 5.4% response, and banner B might only get a 5.1% response, if you're following me there. And that would, in that case, B would actually be losing, not winning, the way it did in this test. So those two ranges are a range of possibilities. Now, like I said, we'll get into this more deeply. Now, the p-value there, you all know about p, right? If you're A/B testing, you know that you need a p-value to be low. It needs to be 0.05. And probably some of you, if you're just running some A/B testing suite, you might just be running your test and looking for that 0.05, and when you get it, you're saying, great, that's 95% confidence. That's low enough. We know that we have a winner here. So you can see in this example, P is 0.12. It's too high. We don't have confidence, according to the typical conventional wisdom with A/B testing these days, which we are about to challenge. And then that last piece of information there is the improvement of B over A, but also, which is 10% in this actual case. But if you do a little math on those two ranges of success rates, what you get is a total range of possibilities of B over A of being negative 2.4%, it actually losing by a little bit, all the way up to 22%, winning by 22%. Okay,
and
so
that's the range that you're really going to want to care about in the future.
Yeah, that's the range we care about. Sorry, go ahead.
That's it.
Okay. Yeah, that's the range we care about. We're thinking about how much is our best banner winning by, or our control losing by, or whatever. Okay, so now we're going to wade into this controversy. Probably some of you have heard that when it comes to determining sample size, in other words, you can see we've got 10,000 banner impressions for each banner here in this example. Well, is that sample big enough for us to trust these results? How do we figure that out? And so there's a school of thought that's been pushed lately that says that you are not that you need to just choose your sample size in advance, and it can often be hard to figure out what those folks how those folks are saying you should go about determining your sample size. But through using some means, you're supposed to determine your sample size in advance and then don't peak. Most of you probably have heard about this controversy. Well, what we're saying in this presentation is that it is okay to peak. And we know that maybe a few of you might be throwing tomatoes at your screen, but we're forging onward. Now, so this was something sort of raised in the A/B testing world by a few writers, and they said, look, basically you guys, you're all doing your A/B testing wrong. You're sitting there running your A/B testing suites, and you're clicking refresh, refresh, refresh as your test is progressing, and as soon as you get confidence, as soon as P goes below 0.05, you jump up and do the victory dance and replace your control with that new ad or that new design. And that's wrong, because what you're doing is you're lying to yourself. You're throwing yourself off. Okay, so we understand what they're saying, we think, and what they're saying has a lot of truth to it, but the prescription that they're giving you, that we would argue, is actually not helpful, and it's kind of counterproductive. Now, here's how we would like to try and explain that. And we're going to try and explain that by showing you a graph of peaking. And this is a graph that Sahar made up for us, and it basically, and I'm going to ask him to explain this graph since he made it. But basically, this is a graph of exactly what we see as we peak at an A/B test over time, from start to finish.
Yes, this graph is a festival of peaking. So let's go over it. At the x-axis is time, or more specifically, it's as we show more banners, what we see. And there are two y-axes, which is a bit confusing, but bear with me. So the red line that you see, the solid red line, is the p-value. And that's what someone would traditionally look at in an A/B test if they're following that conventional wisdom. And so the dotted red line, the horizontal line, is a p-value of 0.05. So if we're signing on to the social convention that you want 95% confidence, you'd have confidence when the solid red line, that's p-value, was below that dotted line of 0.05. So in this graph, which we chose as a really good example, the p-value dips below the line, you gain confidence, and then you lose confidence, and you gain it, and you lose it. So if we were just peaking from time to time, we would be very confused. But if you actually graph it out and look at it over time, you see that the p-value remains, pretty steady actually, in the grand scheme of things.
But if you're right, but you see, this is the you see that I just want to call out that one place there where you see where the red line crosses the green line for the first time. So that is where we first get confidence. And so if we were peaking, which we were, and we wanted to stop the test as soon as we got confidence, and note, which we are not saying that it's that simple. We're not saying just stop as soon as you get confidence. That is not what we're saying at all. But this is we're trying to illustrate the problem that the no peaking police are trying to warn you against. They're trying to warn you against this situation where you get confidence for a little bit, but then you lose confidence and in this case we lost confidence for just about the whole rest of the test.
Mm-hmm. And what we're saying is we want you to de-emphasize that red line and instead have you look at the purple and green lines. And the purple and green lines are the upper and lower bound of the confidence interval of how much D beat A. In other words, they're that rightmost part of the screen for the slide we saw earlier.
Yeah. And so now maybe we should go on to the. So yeah, and now let's try to explain this concept of the confidence interval a little more clearly. And this is going to this whole talk and the way we're throwing around these statistical concepts and sort of abusing them a little bit is making a lot of academics cringe, or a few anyways, depending on how many are on the call. So we just want to, make a disclaimer. We understand that, but what we're trying to do is come to a practical understanding of what these concepts actually mean to us as A/B testers. So let's go back to that concept of running the test over and over and over again in alternate universes, or just throughout the day under similar conditions. Let's say, so this graph, what we did is we went into R, which is a statistical package that we use to support our program, and we told R to generate random data, randomly to generate random distributions of data. In other words, so see, I'm trying to use the statistical terms, and it's just I'm misusing them, and it's not making any sense to half of you too. But what we basically told the statistical package to do is pretend like you simulate a test. It supposedly knows how to do that. It can generate randomly distributed data. And so we say, okay, based on these parameters, which are sort of similar to our test, tell us what a simulated A/B test would look like. And then what we did is we plotted, and we told it to do that 50,000 times. And, it did it in like a half a second. And then we plotted the results of those 50, in this graph, we plotted the results of those 50,000 simulated A/B tests on a graph. And there's no y-axis in this case. We just spread it out so that it wouldn't be one solid line. But you can see that what we have here is we have some banner A beating another banner B by some percentage improvement. So the x-axis is how much in each simulated test A beat B by. And so you can see that little lone dot on the extreme left standing out on its own. That's a case where A actually lost to B by maybe 5% or something. All the rest of the cases, or almost all the rest of the cases, A beat B, and you can see that there's that there's some random variation with each simulated A/B test, and most of the time the tests are, A is beating B by something like 13%. And those dots are falling right there in the middle of the graph. But then there's variation, and so sometimes it's the tests, A is falling a little bit over to the left and a little over to the right. So now one thing to note, so the confidence interval is, let me go back a step. So what the interval in this graph is actually showing, so the purple line is the upper bound and the green line is the lower bound. So at each moment in this test, when we peaked and we got a particular confidence interval, so if you look in the middle of this graph, when we were in the middle of this test, it looks like the purple line is at about 50% or something. So the confidence interval is saying, okay, your winner is winning by somewhere around 0% to 50%. So what that meant was that it was predicting for us, based on these statistical assumptions, that if we reran the test 50,000 times, if we could, under similar circumstances, rerun banner A and banner B for the same amount of time over and over and over again 50,000 times, and then if we were to graph those results, they would be distributed just like this, but from 0 to about 50% is what we saw in the middle of that graph. So we said, okay, great, that all makes sense in theory, but what about in reality? And so this is what Sahar came to help us with over the last year and a half. And we did a whole bunch of experiments like this. And Sahar, maybe you can explain what people are looking at here.
Sure. So we ran one test for a really, really long time. Often we can get enough results within an hour. We ran this for, I think, 2 weeks. And then what we did was we said, okay, we have this really long test. What if we chopped it up into small slices? So it's as if we ran, 30 tests one after the other. And since we ran this test for so long, we had a pretty good idea of what the real value was. But we said, okay, given each test, how much did AEB buy in each of these 30 tests? And then we just plotted them. And lo and behold, we get the same sort of graph that we would, and the stats would suggest. Most of the time, we get a result in the middle, which means that most of the time the results would come out the same, and then they were sort of dropped off in a bell curve from that average. So this is the exact same shape that a statistical testing package would have predicted with any one of the tests.
Yeah, and sorry, the bell curve, we're adding a new twist there with that line. It makes it maybe a little confusing, but if you just look at the dots down there at the bottom, compare that to this pattern. So you can see there's a distribution where most of the line is just showing you the actual concentration of dots at each point in that graph. So you can see they are concentrated around the center of that range. And so we looked at, we have a bunch of data over the years, a bunch of tests, that where we just left two banners up for a long time and we were able to go back and slice it up like this. And so, and this is similar to what, statisticians, when they try to prove their theories, they sometimes go and try and apply their methods to actual data. And so as far as I understand it, I went and looked and found some cases like this where statisticians were actually, writing their PhD dissertations and writing important papers saying, okay, look, we found this data set and we did exactly this. And I believe it's called a Monte Carlo simulation in statistics. And what we would really love is if there's some statistics PhD candidate out there who would like to come and study our data, because unlike a lot of companies, we're able to just publish this data. So this would, we've got a lot of data. It would be great if statisticians came and kind of played around with it. Okay, so we're going to, now we know this is probably still not completely making sense. We're going to come back to it. We're going to rehash it in a couple of new ways, but just to kind of restate what we're saying here, this is the practical lesson. So even if you're not totally tracking the content of these concepts, if you are satisfied to just temporarily try to trust us and go with this with your own program, this is the takeaway that this is one of the few takeaways that we're trying to give you, that not only is it okay to peak as you test, but you don't even have to wait for 95% confidence. And we haven't totally called that out yet, but you might have already picked up on that implication of what we're saying. So, okay, so actually, sorry, this is sort of an additional concept that we're throwing on top here. So what we're saying is that there's no magic at p equals 0.05 or p equals 0.01 that, at 95% confidence or 99% confidence. Those are just social conventions. And that actually every p value has something to tell you. And so, for example, if you run a test and you run it for a long time and p is not going down, it's just sort of staying where it is, and p is equal to 0.3, well, that actually means something. What it means is that you probably have a winner. Or if you get 0.8, that doesn't mean, this test is a failure, we have no confidence. No, it actually means that there's really no difference between, there's probably no big difference between the two things that you're testing against each other. So how can we say that? Okay, so if you look at the confidence interval again, hopefully you're sort of used to looking at these graph bars now. You see where the red line, where P is the red line, you see how for most of the tests we've lost confidence. It's above the red dotted line, which is 0.05, 95% confidence. And so the red line is above 0.05. So now what we had people telling us, we had, stats experts and people that, A/B testing people, we had them saying, you just need to ignore it, don't ever think about it again if you don't have 95% confidence, because otherwise you're standing a chance of lying to yourself and misleading yourself. Well, we disagree now, because if you instead of worrying about whether you're on one side or the other of that 95% confidence social convention, instead look at the confidence interval, where that which represents the range of possibilities of the outcome of your test. So look, if you can imagine those little dots, imagine rerunning this test 100 times, and imagine a little line of dots distributed between the purple line and the green line, in one slice of that graph. Well, if that represents the possible realities, which you're trying to guess at, which you're trying to estimate, just about all, even when you've lost confidence, almost all of those possibilities are above 0%. So you've got one banner winning in almost all of those possibilities. And in a lot of cases, it's winning by quite a lot. And if you remember the distribution that we showed you, where most of the dots were at the center, it's not even equally likely that your true, quote unquote, true reality is down there. It's not just as likely that it's down by the green line or up by the purple line or anywhere in between, but it's actually most likely that it's somewhere in the middle. And then for some reason we've had academics come to us after we say this at a conference, and they, no, that's not true. Confidence intervals don't imply anything about, you can't make any assumptions about what's inside the confidence interval. And we don't understand why they're saying that, because in our actual data and in the data, that's generated by R, and so I think there's sort of a philosophical or social convention reason to not make assumptions about about what's going on inside the confidence interval. But if you're just A/B testing, and this is sort of our main point, and not trying to cure cancer, then don't worry about it. So Okay, so just another way of hammering home this point is it okay to peak? Yes, it is, really. Let's think it through. So what if you peak during a moment when you've falsely gotten 95% confidence, thanks to a handful of anomalous sales or responses? And that's like the example we showed you earlier, where it dipped falsely into 95% confidence for a moment. Well, so what if you do that? And what if the true confidence, if you were to run, is only 90%? In other words, if you ran the test much longer, that you'd eventually only get a 90% confidence, which was pretty much the case with that example that we showed you earlier. Okay, so what are you risking in that case? So you are mistakenly thinking that you have a 2.5% chance of picking the loser when you actually have a 5% chance of picking the loser. So we're saying big deal. And now why 2.5%? Because if you have 95% confidence, if you're wrong, if you're actually falling I'm abusing the terms again, but, like let's say that reality is actually outside of the bounds of the 95% confidence. Well, there's a 2.5% chance that it's above, that you're on the winning side, and a 2.5% chance that you're below, down on the losing side. And so we don't actually care if we're wrong on the winning side. That's great. We just care if we're wrong on the losing side. And that, so in this case, let's say it's the true confidence is 90%. And so you're mistakenly thinking that you have 95% confidence. Well, that's okay. You're just taking a 5% chance of picking the loser. And it's not even probably losing by very much, as you saw in the earlier graph. Okay, so that's what you're risking losing. But here's what you gain. You can move on to test something new. So instead of just, beating your brains out on this test, trying to get something, trying to get better confidence, you should just move on and go ahead and choose the one that seems to be winning, because again, we're not trying to cure cancer, and move on and try to find something that is going to make a huge difference. So go for it. And as long as you're testing frequently, if you're making an error, it will soon be rooted out if you're testing often enough. Okay, well, the good question to ask, and we were asked this when we presented at Strata at this point in the presentation, was, okay, well, that's fine if you are, erring with a 90% confidence, but what if you're erring with a 70% confidence? Okay, let's think that through. So we're saying that yes, it's okay to stop at 70% confidence. Let's think it through. So that just means that you're taking a 15% chance of hurting performance. In other words, a 15% chance that you're using A/B testing for evil instead of good. Oh no! And so before any academics start hyperventilating about that, and to be fair, the academics don't hyperventilate. It's more like it's more like the non-academics who are starting to fancy themselves academics. And so before they start hyperventilating, if you are hurting performance, chances are you're only hurting it by 1% or 2%. Right? There's only a tiny chance that you're doing serious harm. And remember, you're only doing harm to your sales, and only for a short time if you keep, as long as you're continuously testing and changing your design. So remember, we're not landing somebody on the moon. We're just playing with a website. So we put this slide here in case, in the live presentation, in case there was any questions so that we could refer to it about what we just said. But I think maybe it's helpful to you, but let's move on to what we brought. One of the things we brought Sahar on to do was to actually test these ideas against our actual data. And here's what he found.
So thank you, Zach. So I picked out 214 tests where we were really confident about our answer. We ran them for much longer than we needed to, and we had some sort of, we know what the winner actually was.
And so, by which you mean that by the end of the test, we had like 0.01% confidence or something like that.
Yeah.
Okay.
And so then we said, what if we had stopped earlier? What if we had stopped the test at the first sign of 70% confidence after 15 donations? And that 15 donations I'll explain why later. So this is a really reckless time to stop a test. This is way earlier than we normally would have. If we had done that, we'd have still picked the winner 90% of the time, and we'd have picked the loser 10% of the time, which we were okay with, because if we did that, we could have had 3.5 times more tests, because our tests on average were 72% too long. That means 3.5 times more chances to find a huge breakthrough, which is great. And yeah, that is. We don't actually stop at 70% confidence in real life with our tests, but even if we were that reckless, we'd still make that big of a gain. And so now we have another really interesting thing that we figured out. And, it took us a while when we talked to consultants or experts on this. They never really saw fit to mention it until this one guy, Jeff Sorrow, who really helped us straighten this out. And by definition, when the lower bound of the confidence interval crosses 0, we have confidence. And this has just really cleared out our thinking. Zach, do you have more to say on this?
Yeah. The reason we put this in here, obviously we didn't figure this out. This is something that any person who does stats knows, but who professionally does stats, but for 2.5 years, until Jeff Sorrow pointed this out sort of casually in an offhand comment, it had never occurred to me. And this, for me, it was like one of those moments when when finally I understood the relationship between the p-value and the confidence intervals, and how the 95% or the 99% confidence is really just a social convention. And I was just looking at the Q&As that are coming in. Please ask us. We've gotten through the bulk of our material, so please ask us any questions. And if there are any questions that we can answer, we'll switch over to answering questions at this point. But the one question that's up there now that I see is from somebody who said, can we recommend a good book that explains the underlying statistics? And this person has studied statistics, she says, and actually quite a lot, but she still finds it difficult to relate to the somewhat hairy theory of A-B split testing practice, which is exactly our point. We had exactly the same experience. And so this was one of the concepts that just really knocked it into place for me. So, and here, we'll illustrate it using one of these graphs again. Same graph, I guess. And by the way, if you enjoy looking at this graph, Sahar has an application that we're about to launch, which basically goes through almost 1,000 tests, I believe, 1,000 of our A/B tests that we've done over the past few years, and gives you one of these graphs for each one of those tests, and a whole lot of other graphs too to go along with it to analyze it. And you can see screenshots of the two banners. So stay tuned for that. If you just Google Wikimedia and fundraising, and you'll find our fundraising page, and you'll just keep an eye on it, and you'll be able to see it appear there eventually. Okay, sorry, that was like 2 tangents in the middle of this one answer to a question. But so this idea of the p-value of losing confidence when the lower bound of the confidence interval crosses 0. So just take a look at this, and I bet a lot of you will have an aha moment right here. A lot of you who've been confused by these stats. Look at the green line. As soon as it crosses 0, the red line crosses the 0.05 confidence red dotted line. And that's true every time. Every time it goes above 0, we gain confidence. Every time it goes below 0, it loses confidence. What a coincidence. No, it's not a coincidence. That's the definition of getting confidence. because this confidence interval is calculated on 95% confidence, because that's what we told the program to do, so we told R to do, and because the p-value is then the p-value is crossing 0.05 or 95% confidence every time the lower bound goes below 0. So what P is telling us is there a winner? And part of the reason, so P is telling us that based on the criteria that we've asked for, 95% confident, is P or is the winning banner a winner? And so that's all it's showing us here. I hope that's making sense. I know it's a little tortured, but part of the reason why this is so hard to kind of grok when you're talking to stats people is they don't talk in terms of winners and losers. So as A/B testers, we think in terms of winning banners and losing banners, or winning designs and losing designs. But stats people do not think in terms of winners and losers. They talk in terms of difference and difference by chance. And then they start talking about the null hypothesis, and then it just becomes completely impossible to understand what they're talking about. So we did get our heads around that, at least for a few fleeting moments, and we spent time with stats people who could, kind of cross over and speak our language, Jeff Sorrow being the best among them, and that we've worked with, and we tried out this logic on them, and they said yes, you've got it. So hopefully we've got it. And Sahar, to answer Jan's question, what's the name of Jeff's book that we can recommend?
The name of the book is Measuring Usability by Jeff.
Oh yeah, Measuring.
And someone else. Measuring Usability, highly recommended.
Yeah. Okay, so let's see. I don't think there are any other questions. Please ask us a question if you have one. But we have a few more slides, and so we'll just continue for the next 10 minutes or so. So this is another sort of, we're sort of summing up our takeaways now. So this is kind of what we're saying. P is nice, but confidence interval is where it's at. You really should be looking at confidence intervals and pay attention to those, not just your p-value. Thanks. I thought I advanced the slide and I hadn't. Another takeaway is just repeating. There's no cliff at 95% or 99% confidence. It's just a social convention. And, particle physicists, in order to get a paper published, have to get not 99% confidence, but, some ridiculous level of confidence, 99.9999999 forever. And so it's a social convention, but the way we experience these social conventions is as a binary outcome, which is wrong for us as A/B testers. If you're a particle physicist or a biologist, there's a real reason why you experience this as binary, because if you have statistical significance according to the social convention of the journal you're trying to publish in, then you get published. If you don't have it, you don't get published. And so you don't care if you don't have significance. If you're a drug company who is who's just tested a drug, and if you only have 99% confidence that you're not killing some of the people that are taking your drug, then that's not good enough. There's a social convention that they've established for that kind of application. And but we're just messing with websites, and so it's totally okay because again, just to bring this graph, I hope this graph is making sense to you guys. It's hard to do this, without being in front of an audience and understanding whether they're grokking it or not. But remember, all we're risking is that we're falling. That we might, in this case, in this particular test, all we're risking is that we're falling somewhere between 0 and the green line, those places where the green line is going below 0. That's all we're risking. we're just risking losing by a little bit. Okay, why don't we, since I think we still don't have any questions.
4 questions.
Oh, we do? Okay, I'm not seeing them for some reason. Oh, I need to hit refresh. Okay, well, why don't you want to, I still can't see them actually, so, oh no, wait, okay. Sorry, everybody. Okay, so we've got a question. Statistical tests make assumptions about the underlying distribution. In other words, normal versus something really skewed. Banner ads seem like they could easily be a love it or hate it skewed sort of thing. How much does that matter? Okay, that's a great question, and yeah, we really should have brought that up. One of the assumptions that statistics is making, when we use these methods, these methods only apply to a certain kind of data, and that data it only applies to data that is normally distributed. And for me, this is one of the most frustrating concepts because what in the world does that mean? So we spent a lot of time trying to make sure we understood what that meant. And basically what it means is if you remember the graph that we showed before where most of the outcomes were coming in the middle and most were coming off to the side, well, that's normally distributed data. It's if there's an assumption that that basically it's like rolling dice or flipping a coin. It's random, and that there isn't. And I know I'm doing a terrible job of explaining this, and again, the academics are like cringing. But here's what it all comes down to: is as a practical matter, what we did is you can actually do tests on your data to make sure that it is normal. Now, when you're dealing with what's called binomial data, which is like coin flipping or did you get a donation or didn't you get a donation, this is where it kind of gets confusing because when you actually try to figure out whether that data is normal or not, at least we couldn't find any clear way of just like taking data from one test and seeing whether it was normal or not. So what we did, like we showed you earlier, is we ran tests over and over and over again, and we took really long tests and chopped them up into lots of little subtests, like we showed you earlier, and then we graphed those outcomes. And it is easy to create, a graph, a distribution, and then ask statistical packages whether that's normal, and you can just look at it and see whether it's normal. And basically, we were able to satisfy ourselves that our data was normal. And you can do that too with your data. Now, what I'll tell you is, if you're willing to trust me on this, your data is normal. If people are coming and either doing things or not doing things on your website, your data is normal. It doesn't matter if it's like a love it or hate it thing. That's not what it's about. But you can find this out for sure by putting up a test for a really, really long time, and then like for a month or something, if you can spare it, or depending on your traffic, just get a big sample. Maybe that's a day for you, or maybe that's a month, and then chop it up by days if you've done a month, or chop it up randomly. Just mix all the data in together and chop it up into randomized segments, and then pretend that each one of those segments was a separate test and see where the outcomes fall. And you'll be able to see whether or not you have normal data or not. But, or just suffice it to say that if you're dealing with people messing around with your website, you've got normal data. Is that fair to say, Sahar, do you think?
Yeah, or binomial data.
Yeah. Well, okay, so what if I don't have, here's another question. What if I don't have as many samples as 100,000 web page views? Let's say I'm trying to do an A/B test on an email send, where it's difficult to send lots of different messages. Yeah, in our case, we have the advantage that we've got tons of traffic, but we've got a huge disadvantage that our response rate is incredibly low. And so if you're sending out an email send, your response rate is going to be like, if you're sending out an email send asking people to click to read something or to buy something, your response rate is probably going to be massively higher than ours. And the good news is and actually this is another practical thing that was really helpful to us, that to know that the higher your response rate, the easier it is to get confidence and in your testing, I should say the easier it is to get a meaningful test and in a fairly narrow confidence interval. So just because you don't have so actually, like when we were bringing some of our huge numbers, millions of banner impressions, when we were bringing those to some of these consultants that we were trying to learn from, they were shocked. They had never seen numbers like this, but at the same time, they had never seen response rates as low as ours. What they're often used to is like with usability tests. If it's like, do you want, like on a usability test where people are going to do something often, and maybe you want them to do B instead of A, and you're trying to get them to choose B over A, but they're going to choose something. And in those situations, you're often able to get confidence at a much, much lower, with just a few hundred trials. And this is something that Sahara alluded to earlier, was your ability to get confidence doesn't depend on how many trials you have all that much. What it really depends on is how many successes you have and the difference between your successes. What you should do to really develop a better understanding of this is go to an A/B testing calculator. Go to that one that we showed at Thumbtack, and just start putting in numbers. And just put in fake numbers of tests that you're imagining. And one thing you can do is put in 50 successes and 60 successes, and then put in 100 trials and 100 trials, and calculate the results. Then go back and add a 0 to the number of trials. And so go do 1,000 trials each, then do 10,000 trials each, then do 1,000,000 trials each. And look at how little it actually changes the confidence that you're getting. And so that's an interesting thing. And that's also another good way to develop better understanding of these concepts, is to just play around with the numbers, which you can just do with a simple calculator like that. If you can get into R and start generating simulated data, and just asking questions like, what if it came out like this? What if this was our response rate? What if this was our sample size? And look at the results and graph the results. That's a great way to sort of get your head around these concepts. Okay. One more question. What you're saying is hypothesis testing. Are you going to compare it with Bandit algorithms? Well, this is how, when we do this presentation, people always come up and they say, you should really be doing Bandit stuff. And I think what you mean is that we should be testing a whole bunch of things and at the same time, and then promoting the ones that are doing well and reducing the ones that are not doing so well. And so there's all sorts of really complex, cool ways that you can make your A/B testing program more sophisticated. And this might be a valuable takeaway for you guys. I know that most of you are operating in a really different circumstance than us. You've got a website with like lots of different things that you're testing, and you've got a whole bunch of different ideas and options that you want to test, and so you just throw them all up there, and hopefully you've got a statistical A/B testing package that lets you do some complex testing, and will automatically promote the ones that are doing well and demote the ones that are not doing so well. I think that we were blessed, so I'm not criticizing that at all. That is awesome to be able to do that. But this might be a valuable takeaway from our experience, is we were kind of blessed to not have access to that technology. are dealing, at Wikimedia, we're dealing with some very, old technology, and we're dealing with constraints like we can only use open source free software. And just because everything is sort of done in-house on this kind of complex, interesting, and strange platform, we weren't able to use the kind of products that probably a lot of you guys are using. But the reason I say we were blessed to be forced to use this very simple system was because it got us really close, like just to reality and to our users. So putting up A versus B and seeing which one won, and then coming up with an idea and testing it against one other idea, and just doing that over and over and over again every single day, that process allowed us to really get to know who our users were and what they responded to. And then we supplemented that by doing like 1 million surveys of our users, and we went out and did focus groups with our users in person all over the world. And that was really critical too. And the feedback loop between talking to our users and surveying them, and then in those focus groups we would come up with ideas and we would test them out right away against the very best thing that we had. And something about the simplicity of that process was very valuable. Okay, so, but yes, I wish the one-arm bandit and multi-arm bandit testing, and I wish we could do that, but we really don't have much to say about that because we're not able to do it. Okay, so Sahar, do you want to take another one of the questions?
Sure. So Jen asks, do you have any lower bounds on how many page views that are needed to provide some valid statistical arguments? And part of what we're saying is no, not really. If you have very low page views, then what you'll have are really big confidence intervals. If you don't have much data, maybe it'll say, A beats B somewhere from -10 to 100. And that's fine. That's real data that you can use. And as you get more page views, the confidence interval will start narrowing. But with one caveat, you can start applying this method right away, and it will be realistic about its limitations because the confidence interval will be really wide until you get more data. And the caveat is this. For a lot of statistical tests of finding confidence, they assume that your sample is, quote, large. And what it boils down to is that you have 15 successes and 15 failures. And that was in Jeff Sorrow's book, and we tested it out, and it actually seems to be the case. There is a complex mathematical reason as to why that's the case that we don't have time to go into. But
well, and it's not that 15. Yeah, it's not that 15 successes is a magic number. It's just a rule of thumb that statisticians go for. And but like Sahar said, we went through and we said, well, what if we had stopped at 15 donations? How often would we have been wrong? And it would have been very seldom that we were wrong. That's not to say that you get a really narrow and meaningful confidence interval after 15 successes, but you can at least be sure that you're. And we in our case, because our response rate is so low, it doesn't seem right to stop at 15. It just doesn't feel right. Like we just get a lot more information if we go beyond 15. But I think if with higher response, 15 might be appropriate. Yeah, but basically, I think, Sahar, what you're saying is that it's not really about. It's sort of, again, it's going back to this thing I said earlier. Is it's not about how many trials you have. It's really, confidence is really determined by how many successes you have. It seems like. Mm-hmm. Okay, did you pick out another question to answer, Sahar? You feel that would be good to answer?
Let me look. Bandits check. Do you not segment results? are you not concerned that certain exogenous variables may be skewing results? E.g., traffic with a higher prior propensity to donate were put in the test, and traffic with a lower prior propensity to donate were put in the control. And so if I may translate this to English a bit to make sure I understand, what Nate Ford is asking is, what if the people who see banner A were different sorts of people than the people who saw banner B? And that is, in fact, a good point. And what we found is a lot of the like if you get weird results with your, for your tests, often the problem is not the math you're using, but the data that you're getting is somehow bad. The way we dealt with the people who saw banner A and people who saw banner B being the same is, in the back end, people are given a random cookie, and there's a whole process to deal with it that your A/B testing package should take care of for you.
Yeah, but actually that's a really great question, because we did have a problem, because the way we were doing it, at one point we realized that the way we were dividing the traffic, we added a new feature to allow us to do something. I won't go into it, it'll take too long, and we realized that was creating the exact problem that you just mentioned by a little bit. It wasn't going to be a huge skew, but it was going to be a little bit of a skew. Now, the only reason we figured that out was because we are insanely paranoid about our own mistakes, and we're convinced that we're always making mistakes every day. And I think that again is another danger of the fancy stats pack or A/B testing packages, that kind of do everything for you, because it's just too easy to click, to get the click, show me the results, and you get the results and you trust them, and it's fine. And sort of because our system is sort of so clunky and kludgy, it forced us to be just completely paranoid all the time. And so we were always digging into the data. I was always running my own queries on the underlying data to just see if I could, prove our tech folks wrong. And, they justifiably came to hate me because my whole mission in life was just find the error, find the problem. And so Sahara's queued up some slides to show another way to catch errors like that. Mm-hmm. Go ahead.
So the last big point I would like to leave you with is use diagnostic graphs to detect errors in your testing. So for example, what if banner A just stopped getting shown for a little while? You could dig around in SQL and find it maybe and test every time, or you could have a graph like this that shows banner impressions over time. And as you see, the blue banner just dropped off for a while. Or over here, where someone just completely forgot to turn on the blue banner in countries outside of the U.S. And so we have a whole suite of just diagnostic tests to make sure that banners are being served smoothly, that the countries are being split up evenly, that sort of thing. And you should do that too.
Yeah. Pete, what's another question? What about running a bunch of tests? Oh, we should wrap up. Okay. All right.
All right, let's take one more question, folks. We are over the top of the hour here, so folks, we're going to take one more question because that is all the time we have. And Zach or Sahar, let's take this one here. A few people had this. Can you tell us more about how you segment the groups by IP address, geolocation, time of day, or user ID? How do you make sure you avoid bias? Any lessons learned?
Well, the big thing is when you do a test, you need to make sure that both the groups, are the same. So you need to be taking one group of people and then serving your different treatments to them randomly. And so you can't, and you need to be, as crazy as possible. I think there's pretty much, no exception. You can't allow any any bias difference between the two groups. You have to literally be serving to the to a stream of users randomly, if that makes sense. But I'll give you an example of how I violated that in my first days at Wikipedia, because I made this ridiculous assumption in hindsight that we could compare donation rates from one time of day to another, or from one day to another. So in other words, if we tested A versus B, and we saw the donation rates that A and B both got in that test, and then later on in the day, if we tested C versus D, and we got two different donation rates, I'm talking about, a donation rate, I mean that 2% of the people donated, or 2.2% of the people donated. Well, I assumed that we could compare those rates to each other. So, I assumed that if banner A got a 2% donation rate, that it would always get a 2% donation rate. And it turns out that that is not true. That our, not only, of course, that our traffic varies throughout the day. It gets really low at night and gets really high in the day. But not only that, and so of course the number of donations rises in the day and falls in the night, but the actual donation rate rises and falls. Now, I know that must be obvious because it's part of some of your experience, but probably some of you have not had that experience. And if you're only looking at your data by day, of course you wouldn't see that. So because we were testing so often throughout the day, that turned out to be a huge thing for us. So it turned out that, so that was sort of our slap in the face. That was our lesson. That we absolutely had to, never ever, mix different kinds of people together. So, and also, so I think hopefully that answers the question. Also with Wikipedia, we can run tests by geography, and that's about it. We can also run tests by different projects, so we can run a test on Wikipedia, or on English Wikipedia, or Spanish Wikipedia, or Wiktionary, and our other projects. But we don't track our users. We don't keep that kind of data about our users, and so unlike all of you, we can't run different tests to different populations.
Thank you very much, Zach, for that. There still are actually several folks that are on with us. So, gentlemen, if you want to take the next few minutes and just close out with the remainder of your slides, I think folks would appreciate that. So we'll turn the program back to you.
Okay. We kind of had some extra slides, to use in the case of questions, but we do have a few other sort of tidbits that are probably going to be interesting for people. So let's just run through those pretty quickly. So here's just a few tips. So we're just gonna go through these without huge long explanations. Don't freak out when your P value shoots up for a moment. It's probably just an edge case. Now, you might not have that edge case, but we did. We had some tests like this, where this is sort of the opposite of the other case that we kept showing you. Instead of getting confidence for a second, we lost confidence for a second. Well, we think that this special case in our situation is it comes from our very, very low response rate. And this test in particular, at that particular moment in the test, we were just getting a few donations per hour at night in Russia. And this was a test that went over weeks. And so we went in and we looked at the data minute by minute, and we saw that 5 or 10 donations came in on one of the banners all of a sudden in 1 minute, and that was enough to throw everything off. Now, why did that happen? There was, maybe it was a 1 in a million chance, or maybe it was that somebody tweeted a whole bunch of their friends or sent out an email link, and that again is something that we would hopefully be able to pick up with some of our diagnostic graphs, actually look at the source of some of the things, and you can. So there's the blip closed up, and you can see this is a graph of the banner impressions in that test, and you can see that one of the banners actually got a whole bunch more views during that moment. So actually, I actually don't know how to explain it. The explanation I gave wouldn't explain it. But okay, here's another tip that really helped us. It turns out that to have your confidence interval, you have to roughly quadruple the sample size of your test. And so if you're sitting there, in a test like this, and if you can imagine us sitting there and, P is not changing very much, and, we've got a huge amount of confidence, but, what if we really want to have a narrower confidence interval? Well, we would have to quadruple our sample size. And just, so the experts told us that. Again, it's something that should be like on page 1 of A/B testing stats books, and it's not. It should be, but when people finally told us that, we said, wow, okay. But then we went back and tried to test to see if it was actually true, and sure enough, it is true according to our data. I think we're just showing that in these slides. This might be something that applies to you. Like I already alluded to this, we have wildly fluctuating response rates, and they go really low at night and in countries where we don't get a lot of donations, but we have tons of readers, and they go really high in the day and in countries where we do have a lot of donors. And it seems like that causes some anomalous situations like the one I just covered. And so this is one where we showed this to Jeff Sorrow, actually, and he said, that's not possible. You shouldn't like have P going down and then suddenly going up. And again, we dug into the data and we found that it was a borderline case where where this banner was, just slightly a winner, and we had an incredibly low response rate, so that just a couple of donations coming in 1 minute on one of the banners was enough to throw things off. So if you have very low response rates, just know that weird things might happen. And again, but here's the solution for you is don't worry about P, just look at the confidence interval. And so if you look at the confidence interval there, again, it's the purple line and the green line. Well, what we're actually seeing here is that during that lull in the day, the graph on the left is page views, and so you can see it. We happen to run this test overnight, so the page views went way down, response rate went way down, and so we just completely lost confidence, and we just had noise, right? Until finally the traffic started to pick up, and then we finally got signal again. So if your response rate is just incredibly low, that just might mean that you have noise, and you just need to wait till day. So actually, another practical takeaway is if you're doing, if you're not testing in 24-hour increments, don't test at night unless you're like a video game company, and don't test when your traffic is the lowest. Sahar, why don't you take this one?
Okay. So the next thing that we figured out is that any stats test will do if you're testing the same way that we are. So for example, for a real life sort of situation of this many donations, this many page views, like 95% confidence level, here are 10 different tests, methods for getting a confidence interval. And look, they all give you roughly the same results. And rather than
to back up, some folks might not know what we're talking about because your stats package or your A/B testing package is using one of these methods or something. But if you're actually playing around in R, and if you're wondering which method you should be using, that's what Sahar is talking about here.
Yes, thank you, Zach. So don't worry about it. The method that your stats package is using is fine. Pretty much any method that you could be using in R is fine. If you're worrying about websites and click rates and page views, then any test will do. The difference really comes in when you're dealing with like very maybe like 50 people and just a whole different level of magnitude than what we're testing.
Yeah. We covered the next point, and so I think that's it. We've covered basically all the material that we have. So so thanks everybody for being part of this presentation, and thanks for your questions. We hope you got something out of it. And you can reach us at I'm Zach at ThoughtWorks. I think we have a slide with our contact information down below. Yeah. I'm Zach at thoughtworks.com. There's Sahar's email. And our code and our data, we would love to share it with you. We're in the process of trying to publish a lot of the data online. A lot of stuff's already up there and published, and we would love to collaborate with anybody who thinks they'd be able to help us dig a little deeper or prove us wrong about any of this stuff. We would especially love anybody to clear us up about anything that we've gotten wrong in this presentation.
Great. And with that, folks, wow, what a great webcast we had today. Zach and Sahar, thank you so much for sharing all your knowledge and expertise with us. Folks that attended today, we thank you for attending our event and hope you've benefited from it. And for those of you that sent in your questions, thank you for those questions, because having those really adds so much to our event, so we appreciate it. As we wrap out the program and close it up here, we want to let you all know that next week we do have O'Reilly Strata Conference in Santa Clara, February 11th through the 13th. A couple tickets only remain, so if you have the time, we'd love to have you at the event there. Snap up those tickets because they will be gone. So again, it's February 11th through the 13th, and there's going to be a lot of great presentations there, lots of information, and you don't want to miss it if you can make it. Folks, we're going to close out now. We thank you all for attending and for staying on with us. I know we went a little bit long here, but there's so much great information that Zach and Sahar shared with us, so we do appreciate their time as well. This will conclude our webcast. Goodbye, everybody.